So, on behalf of Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur, I'd like to welcome you all today in this webinar series, mega webinar series, named as the Saturday Manufacturing Talks. We started our journey in the month of March 2021, and today is the 31st week. So every Saturday, 8:30 p.m. In Indian Standard Time, we are getting assembled, and we are very fortunate that we are able to listen to the eminent speakers from India and abroad, from industry and also from the academia. So they are discussing about their experience, research experience in different fields of manufacturing, starting from AI/ML, additive manufacturing, robotics, welding, machining. These days, people talk about the AI/ML Industry 4.0, but sometimes they forget that the fundamentals of the manufacturing, that is, that can't be, the forgotten. Because if you'd like to develop a digital twin, the digital version of the physical systems, you must have the complete understanding about the physical systems itself. So you must have the domain expertise. So we are very fortunate today to have Professor Suhas Joshi. Professor Joshi doesn't need any introduction, but I will just mention some of the key achievements of Professor Joshi, so that you can appreciate that how much effort he has put in and how far he has reached. So Dr. Joshi has been a faculty member at IIT Bombay from 1999. Presently, he is the Rahul Bajaj Chair Professor and also the Dean of Alumni and Corporate Relations at IIT Bombay. Dr. Joshi has worked as a postdoctoral researcher at Georgia Tech in 2002 and served as a visiting faculty of University of Illinois Urbana-Champaign from 2005 to 2006. Dr. Joshi was also head of the Mechanical Engineering Department at IIT Bombay during 2014 to 2017. He has been the recipient of the Boy Scouts Fellowship, Government of India in 2002, Best Faculty Award in Mechanical Engineering Department at IIT Bombay in 2007, and Dr. P.K. Padvardhan Development Award of IIT Bombay in 2008. He has undertaken large number of the research projects, consultancy, and also got involved in the infrastructural development in various fields at IIT Bombay. He has served as the associate editor of Transactions of ASME, Journal of Manufacturing Science and Engineering from 2007 to 2014. So seven years he was there as the associate editor. Presently, he is the associate technical editor of Machining Science and Technology, and Francis, since 2010, and editorial board member of International Journal of Machine Tools and Manufacture, Elsevier, from 2013 to 2018, and Indian Journal of Engineering and Material Sciences from 2015 onwards. Dr. Joshi has supervised large number of doctoral scholars, and presently he is supervising 6 doctoral students for their PhD. He has supervised more than 100 MTech students at IIT Bombay, and he has got the immensely high number of publications, including 177 referred in international journals. So you can see that he has got a tremendously high scholastic, the output in the field of the manufacturing. So with this short, the description of the biosketch of Professor Joshi, and I am requesting Professor Joshi to start giving a lecture on the topic that he has decided.
Thank you, Professor Paul. I think it was a mega introduction. Thank you very much anyway. I will share my file. I am in a presentation and I will start. You are able to see, right?
Yeah, we can see. You please go to the full screen. That's it.
Okay. So, shall I start?
Yes, please. Yes, please.
Oh,
Yeah.
okay. So I'll be talking about a little bit traditional topic of machining of difficult to machine materials, and I have divided. I mean, I have taken a subtopic of physics-based machining in the sense that understanding the several smaller phenomena which happen during the machining processes, and then try to model them. You know, we always find that our uh, experiments are somewhere and our theoretical predictions are pretty away from the experimental results. That is because we have we are not having complete knowledge of the physics of the process. There are many small phenomena which are happening during the processes, and we just don't take them into account while we are modeling. So I titled this as physics based machining of titanium alloys. Why titanium alloys? Because they have typical properties, very high strength and low density, and they have a temperature stability up to 440 degrees centigrade, good corrosion resistance. They are good compatibility with composites and also with the human body. So inertness with the human body. So you can have several implants in the body, titanium implants in the body, and nothing happens to them. So they have got several properties. They generally come in three different forms. Rather I would say many different forms. And the basic form is alpha alloy, which is a HCP structure, and then beta is a BCC structure. So as you go from alpha to alpha plus beta and beta rich alloys, you go from medium strength to medium to high strength and low ductility. And good formability is also another characteristic of beta alloys, whereas good creep resistance at the alpha alloys. So they have good applications in corrosion resistance, where corrosion resistance applications are there. So this is some graphical picture of application of titanium alloys in impellers, fasteners, uh, uh, and the piston, and kind of airframe structures, airframe structures where the whole structure, you take a block of a very large weight, and then you carve out the 90% of the material or 80% of the material and keep only the external frame on it, and rest of the material you just remove. So that kind of material removal is also required. Aluminum frames are also made, but titanium frames are also made by this. Their properties which are causing difficulties in machining. These include their low thermal conductivity. So, though high strength, but their conductivity is low, and that actually causes the problem of heat accumulation during machining process, and the tools get melted or they react heavily during the machining processes. So there is you will find all kinds of wear, abrasion, chemical adhesion, all kinds of wear while you are machining with titanium alloys. High cutting forces and tool breakage or tool melting is also one of the uh, uh, sorry something like this. Yeah, is one of the problems. Low elastic modulus is another issue which they have. You can see the difference between the elastic modulus, it's almost like half of it. So they have a greater spring back while you are machining. So this actually comes into picture while you are tapping the you are creating the internal threads in the titanium alloys. When you are creating internal threads, uh, the material which is cut, it actually springs back. The material which has been already cut actually springs back, and it grips the tab when you go deep inside the hole. And then when it grips the tab, you will not be able to remove, and breakage of tabs is a very common phenomenon. It has other implications also, but this is one major phenomena here. Segmented chip formation is something which happens during this machining, and I will talk about it in little more details. So as I mentioned, there are several microscopic phenomena that occur during machining, and they affect the chip segmentation, chip formation, and physical and mechanical properties of the surfaces which are generated, and consequently the machinability and quality of the surfaces. So this particular symbol on the right hand side on the top actually tells you, shows you a drop of blood from a syringe. The way humans, you can characterize the human blood and tell how the health of a person is, in the same way you can take a chip, a segment of chip, and characterize what is happening in the machining process. So I require only a few segments of chip, and then based on that few segments of chip, I can, in fact, find out the entire characteristics of that particular material. So that's why this kind of a drop of blood I have shown here. If you look at this particular slide, it's a simple slide, but picture, but it is a very complex. It tells you all complex phenomena which happen in a machining process. So, for example, if you take a shear plane, it is the largest consumer of the energy. So, whatever energy you are giving to the tool, and of that energy, the maximum amount of energy is actually consumed by the uh, by the by the shear plane deformation which happens in the shear plane. Very interesting phenomena happen during shear friction, or shear which happens during the machining process. Your strains are of the order of 2 to 8. Temperatures can vary between 100 degrees centigrade to 1100 degrees centigrade during machining of various materials, and the strain rates are 10 to the power 3 to 10 to the power 6 per second, which is common. So let me tell you is that the strain rates signify the strain rates of explosion. When the explosion bombs explode, there the surrounding material is actually displaced at the rate of 3 to the power 3 to 3 to the power 10 to the power 3 to 10 to the power 6 per second. You are performing a normal machining operation, you are pressurizing the material, you are taxing the material, analogous to a bomb blast. You don't realize it, how much you are applying a pressure, stresses, and temperature on the material, but that is something similar to similar to a bomb blast. Similarly, strains, if you take a tensile testing equipment and you undertake a tensile testing, you will find that the specimen will break at a strain of 0. 0.1, 0. 0.2, 0.3, and in a machining process, we invariably subject the material to the strain from 2 to 8. It is all the machining process starts from, it's such a high strains you submit. So essentially it is one of the extreme manufacturing processes that you subject the material to the extreme possible conditions and you try to remove. And then we say that, oh, I don't want damage on the machine surface, so I don't want to use a lot of energy, I want to save my tools, I want to save my machine, so I don't want vibrations, I don't want this. All those things are also possible. You say that I don't want vibrations, you say that I don't want deflection, I don't want everything. Yes, today that technology is available. We call that as single point diamond turning machine. With a single point diamond turning machine, you can make the chips, you can remove the ductile chips from the material which are of the order of few micrometers in thickness. Even that much, the technology has reached to that level that it can slice the material so easily, and so thin slices of the material or chips can be removed. So, but nevertheless, these are the issues they have overcome. But in normal circumstances, when you are machining, you will not be able to use that the most sophisticated machine, but a regular machine, because it is not cost effective to use that kind of machines. You take a interface between chip and tool. There are several phenomena which happen there: two-body friction, three-body friction, crater wear, chemical wear. Many things happen along the chip and tool interface, and whatever the energy required here determines what happens on the primary deformation zone. Take the third deformation zone between tool and the workpiece. When the wedge tool is actually moving, this is again a subject of massive research in the machine technology, and intense friction, heat generation, material separation, severe deformation, heat affected zone, many things come onto it. So each of these zones have been investigated in a great details, and but still there are challenges when the new materials comes, like super alloys, titanium alloys. They put forward massive challenges, and we as a researcher, as an academician, we try to solve those. So the issues are chip segmentation, shear band formation, grain transportation and deformation during the machine surface, during machining, and the deformation of machine surfaces. So it is like Newton's third law. You have equal and opposite reactions. So when you apply a huge force on the chip formation, naturally a chip is separated from the workpiece, and the workpiece will also feel the heat of it, because every action has a reaction. So you gently remove the material, you will find that the material which chip, you will find that the machine surface is also not damaged. So that happens in a diamond turning machining operation. You remove the chip so gently that there is no damage to the machine surface. But if you use a huge force, there's going to be huge damage on the machine surface. So what is that, and how do you prevent? So we have done what we call it as the very extensive kind of experimentation on the titanium machine, thanks to one of my PhD students, or rather several MTech students, and uh, two PhD students who have worked on it. We used all kinds of temperatures, minus 70 degrees centigrade, high temperatures up to 300 degrees centigrade, mist jet cooling, thermally enhanced cooling, increasing temperature. We had 3 different alloys of titanium. Speed, feed are the regular parameters that we can say. So the machining environment, compositional variation, and process parameters, and we try to understand the physics. Like these aspects, we try to understand what are the shear band, spacing, grain size, deformation, and all that, and try to correlate the microstructure of the material and the machinability linkage. Try to understand what happens. As I mentioned, that the way you are cutting, the way you are generating a new surface, how much efforts you give, or how much energy you give from removing the material, some amount that's actually reflected on the machine surfaces. So one of the very traditional tools which is used for understanding the fundamentals of what is happening is that this wedge is moving. Now what we do is that while the wedge is actually moving, we simply take the wedge out from the machining process and let the partially formed chip remain on the surface. Now I'm showing it representatively here, but it is on a turning operation. Say for example, you are turning. What we do is that we take a pin and we rest our tool on this particular pin, and we perform the turning operation. So you are performing a turning operation. The tool is resting on this pin, and at one point, what we do is that we hit the tool from the top so that this pin shears off. This pin shears off, and the tool is actually withdrawn from the machining process. So the tool is resting, and then suddenly the tool is withdrawn, and the chip segment remains attached to the work surface. So you do these experiments in all the conditions: hot conditions, cold conditions, minus 70 degrees centigrade, high temperature, mist cooling. So this objective of this one particular boy was to do only the chip freezing under variety of machining conditions, and try to understand what exactly how the machining process happens. So the frozen chip root, we call it, as it looks something like this, that the chip is partially formed, and it tells you how many segments are formed, how the segments are formed. It's like, you have taken a picture of that particular machining process at a given instance. So now you take this chip, you polish the top surface, you mold it, epoxy, and polish the top surface, and you will find that a large number of things can be visible from here. I'm not going into details. There are many experiments we have performed, but I am trying to give you only the most important aspect of this. So this is one particular frozen chip, and it is the picture of a high magnification picture of the frozen chip, which is kind of surface polished. You can see that the grains here are of a certain size. You can see these are the grains here, and the grains are oriented in a certain direction, and when they transform from the undeformed material to the deformed material into the chip, while they are transforming, you can see that large bands are generated. So the grains are actually elongated while they were here in the material, and when they are pushed inside the chip, they get elongated in this direction. But you will find that you can see that there are grains here. These grains are of similar size over here. There are grains here. These are of something similar size of that, but there are kind of lines here. These are the lines which show that the grains have got elongated in those directions. So these are the lines, these lines show that the grains are elongated in this particular. So you have a 5 or 6 micrometer grain, and now it is gone to become very small size grains. But you also see some of these grains here. So the chip formation in this material is a very different phenomena, and you'll wonder what are the things what happen in this particular case. So this is a EBSD electron backscattered image of the shear zone. So you can, of the again the frozen chip segment, one of the frozen chip segment, you can see that the grains here and their colors indicate the initial size and orientation of the grains, and you can see that this particular over here is something similar what is over here, and here also you find that there is some distortion of the grains, but more or less something similar here. But if you take the zone here in between the two chip segments, you find that there are very fine particles. Now, the time required for formation of one segment could be in microseconds, and microseconds, the whole microstructure which was here something like this has been completely shattered along certain directions, and those directions are these directions. This is the direction of the shear, this is the direction of the shear, and intermittent structure remains more or less intact. Okay, you can see that the intermittent structure remains intact. So there is one segment is formed, and that segment and the previous segment, they rub so intensely that all the grains between the two segments are crushed to a very small size. You just cannot under the EBSD, you just cannot focus on them, because they have become very small. That when you are seeing from the microscope, if something is very small, then if you start focusing on that, the other things will become get out of focus. So within a fraction of microseconds, this whole segment got formed, and you see now the structure here is that but there are some intact grains, but around the grains between the two segments, you find that there is very strong crushing of the grains. So you go a little bit further and try to understand what is happening into this. So you can see that this is a portion. This portion is nothing but this portion is nothing but this portion. Okay, what I'm trying to show in that figure is the portion over here and the portion over here along the two segments, on this side of the segment and this other side of the segment. So this is the segment which was there initially internally, and this is the between the segments, and this is between the segments. So parent material and the segment is this, and the segment and the previous segment and this material is this. So you can see that internal microstructure of the segment and their grain sizes are more or less similar. Only those grains which are there on the sides, on this side, you can see that these grains are elongated and these grains are completely crushed. They are crushed beyond recognition, sort of. So if you enlarge this section, you will find that these grains are not focusable. So their sizes are of the order of 20 nanometers. So you can now, these grains are of the order of 5 to 6 micrometers. They were of 5 to 6 micrometers, and within a microsecond, their size has got reduced from 5 micrometers to 20 nanometers. 3 orders of magnitude difference within no time. I mean, within a very, very small time. So now, when we are trying to model how much amount of energy is required for the machining process in the titanium alloys, unless we understand this crushing process, we will not be able to calculate the energy. We will not be able to model this energy required for the deformation of the material, because this is a completely different, it's not a machining, it is not a machining process. It's kind of, it is also an extreme powder metallurgy. You crush the material to a very fine particles. So that is where it comes, that where your energy is going, you are pushing the tool and trying to machine where your energy is going. Energy is in a titanium alloy is going in, maximum amount of energy is going in crushing the particles and forming those gaps. These black bands, what you are talking about is the black bands which are created. That this happens because the material has a low thermal conductivity, so it doesn't allow the heat to transfer. The heat remains accumulated and it crushes the particles, because of which you can crush the particles into very small size. Now, if you take the zone which is very close to the tool point, and the tool was moving very close to the tool point and trying to see what is happening there, this is a transmission electron microscopy. So what we have done is that the segment which is over here, okay, maybe I'll show you here, this particular place, at this particular place, this segment was of thickness, say 2 millimeter. We have reduced its thickness to, say, 100 micrometers or even smaller, so that we can focus and focus on this particular part and see the crystal structure there. Now, we call that as a transmission electron microscopy. Now, when you do this kind of course, you have to make a small hole there and do a polishing operations, and then you can pass the electron beam and try to see the structure, what has happened. So this actually shows that these particular locations in front of the tool are completely filled with kind of dislocations. So there are piles of dislocations in these zones, and they tell you that why the energy required for the deformation is very high. Now, this is another experiment that polished chips, you can etch them, and while you are etching them, where there is a valley, there is a gap between the two segments, and then at that particular location you will find that the pointer the itching it creates a deep valley there, because those zones, during the itching process where there are very fine grains, those itching happens at a rapid rate, and that's where you can see that large valleys are formed at those locations, whereas in the segments of the chips you will not have that high rate of itching. So it confirms that yes, there is a very fine grain formation. So one another thing which I want to point out here is that this problem is not solved, whether we are saying something and the literature they are saying something. So we say that there is no recrystallization of the material, even though there is a crushing of the particles. We don't find the formation of a new material there, and but it is confirmed by some other authors. But some other authors say that find that no, there is a new material formation. So we leave it there. We compare and we say that yes, we differ from your views, but yeah, we differ and we have experimental evidence. They have the experimental evidence, so it is the question is still open, that whether there is a dynamic recrystallization during the formation of the shear bands or not. So this particular figure talks about three different alloys: alpha, alpha plus beta, and beta rich alloy. As I mentioned, the three alloys are there. So in a alpha alloy, which is relatively softer, you find that this non-indexed region is very small, whereas alpha plus beta, which is an intermediate alloy, this region is large, whereas the beta rich alloy, this index is very large. Non-indexed region is very large. So this what it means is that the a large number of grains, when you are machining, a large number of grains are getting strained beyond their plastic limits, so that they don't recover back. Their strain recovery is very limited. So which means that the material undergoes excessive plastic deformation while it is getting formed. This is some slides on talking about machining at high temperatures and low temperatures, but I will show you here the chips which are formed. So any segment will have something like, if this is the total length of AB, the total length of shear plane, then A to C is a plastic strain, and between B and C is a kind of a fracture. So this is what is the situation. So this particular segment is formed, and you can see that there is a friction and there is a band, whereas the internal microstructure remains more or less same as that of the base material, and there is a severe band formation at these two ends, between the two segments. So the relative contribution of two mechanisms, plastic deformation and fracture, is proportional to the length of the separated region. So whatever is the length, that proportionately tells that there is a fracture is this much and plastic deformation is this much during this formation. So this is another chip segment which is frozen, and it's actually the SEM photograph of this. You can say that these kinds of segments are formed during the machining process, and that's where the shear bands are formed. And then these are the cracked regions, in each segment. While it is formed, a part of it is cracked and part of it is plastically deformed. So that's how the different mechanism happens. So this is a picture of chip, not the frozen chip, but actual chip, and at room temperature, under minus 70 degrees centigrade, under liquid nitrogen, and at about 260 degrees centigrade high temperature. So you find that the segments which are formed are sort of this kind of a trapezoidal. This is a trapezoidal type of a segment. But when it comes to the LN2, under LN2, it's kind of a semi-circular kind of a segment is formed. And when it comes to high temperature, you have a significant deformation of this trapezoid, and irregular trapezoidal kind of a segment is formed. But if you look at the mechanism which is happening, so the mechanism remains mode 2, that is a shear kind of a fracture in the room temperature, and as well as at the high temperature. But at the low temperatures, LN2, it is like it's like mode 1 kind of fracture. It is like is pulling these two segments apart. Other one, it's like a mode 2 type of the fracture, which is the shear type of fracture. So this we call it as the tear, and this we call it as the shear. So this is shear and this is tear. So mythology, that Jarasandha, the Jarasandha has been torn apart and then only he died, something like that. So this is like tear and this is shear. But at higher cutting speeds, you have a larger fracture length, which is happening here. You have a very large fracture length, which happens here. That earlier figures were at lower cutting speeds, but higher speeds, the fracture length increases. So you have a larger portion of the segment which is formed is by this fracture. So when you have a segment which is actually cold, the tool and the workpiece which are at minus 60 degrees centigrade, and then you start machining, what happens is that there are two fronts in a segment which are formed. One is called, this is a colder segment section of the hotter, because the tool is coming from this side and it is applying the energy, whereas this is the colder section of the front section is the colder. So the front section deforms in a brittle way, whereas the lateral section, which is at higher temperature, deforms in a plastic way. So that's how you get that kind of a semicircular kind of a segment. This is the crack formation or the fracture which comes up to a certain level, and then there is a folding of the material or folding of the shear plane, which happens during the subsequent part, and that's how it gets a semicircular kind of segments. So we have done a lot of study on this, that all the segments and their shapes are actually superimposed on all the parametric conditions, all the machining environments and all that, and a huge understanding of the segment formation, each segment, how it is formed, what are the shapes, and how the shapes change between when you change parameters, when you change the processing conditions, when you change environment, what happens. So all those, this is like one example of what happens to at LN2 and lower speed, and at 260 at higher speeds, how the segments actually change their shapes. This is one example. Don't want to go into details. This is a segment ratio, segmentation frequency, but I don't want to tell much about that. At the lower speeds, at room temperature, at lower speeds, generally the shear bands are thinner. You can say that at the room temperature, high temperature, you get a band which is thin. Whereas at higher speeds of 98, 91, around 90 meters per minute, you get prominent cracks which are formed during LN2. So you can see that the chips are getting cracked during the machining process. As I said, that the fracture becomes very prominent at higher cutting speeds. Also, while you are doing all those damages and all those things on the chip material, the chip is actually separated from the work surface. So what is happening to the work surface? You are taking out one fraction of the surface, and then what is happening out of the surface? So if you want to quantify the distortion of the grains on the surface, then you can do it by means of finding out the slope of these lines, these grain lines, delta by L, tan theta equal to delta by L, and this theta gives you the severity of the strains. So the strain beneath the surface, you can see that there are larger strains at room temperature. Ln2, the strains are lower, and obviously at the high temperature, the strains are much smaller because uh, maybe depth of machining. This is one particular picture. We use it as a sort of a landmark picture. This looks like a beautifully woven carpet, but it's a picture of machined surface of titanium, and you can see that up to here the grains are elongated, and after this the grains are uh, more or less globular in shape. So that's where we call this as the machining affected zone, and we quantify the machining affected zone in all these cases. So I'll not go further details. There are many things, but I'll tell you few another couple of interesting things, and then I'll stop maybe another 5 minutes or 7 minutes. Um, Often we encounter that the drilling process generates a lot of burrs. Now, what we did here in this particular case is that we made a very good setup in such a way that the entire drilling process can be visualized by a camera from the bottom. And you can see now that this particular this particular row, each row here is actually the photographs. Like we stop the process and take the photographs. It's like a video, and we have taken out the photographs at various instances. What exactly is happening during the process? So while the chisel edge of the drill is coming out, it has come out from here, and then it has come out. You can see that up to a greater extent, while the drill point is inside the work surface, the chisel edge is already out, the drill point is already out, but the cap is getting broken. So in this case, you will find that there are two caps are formed. One small cap which is around the chisel edge, which is formed first, and then the entire that cap chisel edge cap is here. Sometimes the chisel edge cap get dissociated, or it remains there itself, and then the entire whole cap of the whole hole is formed, and then in such cases you will find that when this kind of a bigger cap is formed, a part of the cap remains here, but you can see now extremely strong and rigid burr which is formed around the periphery of the hole. You can see here at different speeds, 800, 1000 rotational speeds, that a small cap is formed at the beginning, and then a larger cap is formed at the periphery of the drill, and then after some time this cap is dismantled, but it leaves a very tight burr. It's a very strong, it's an extremely strain hardened material. So it forms this strong burr is formed. So now the phenomena is something like this. You are drilling, and you reach to a situation that the thickness of the bottom plate has come down. It has become very small, and it is not able to sustain the drilling thrust. While it is not able to sustain the drilling thrust, it starts bending. And while the cutting edges are cutting, the lips of the drills are cutting on the sideways, the chisel edge is doing nothing, and simply pressing this whole cap downwards, and because of the rotation, this small piece of the cap comes out. Small cap comes out. You can see this as small cap coming out, and the moment the drill corner comes to the end of the plate, you will find that there is the whole the drill cap, broken drill cap comes out, and it leaves a very strong burr on the corners. So we took almost like 50-70 probably the videos of this, and then we were able to actually come out with a very nice picture of the what happens during this. I have videos, but somehow I'm not able to locate today these videos. But we could get the several phenomena which happen during the process of drilling by this way. I can explain you little more during the modeling. Now, what we did was we made a change in the geometry of the drill. What we did here is that we reduced the length of the chisel edge. You can see here the length of the chisel edge is quite large. We reduced here the length of the chisel edge. We also we gave a chamfer on the drill corner. So you can see here in this case, this corner is relatively sharp. Now what we did is that we gave a chamfer on the corner and we reduced the length of the chisel edge. Now you see the difference. What happens here is that the chisel edge being smaller in length, it doesn't pierce the cap now. The cap entirely remains intact, and to the extent that the cap comes out from the body completely, and it remains intact. So in the process, you will find that the burr which is formed on the hole is also uneven, but it is much smaller as compared to the earlier holes. The other issue which we found is that because of this, the temperature of the cap has increased, and you hardly found anything red hot here. Maybe at higher 1000 RPM, this was becoming like kind of reddish, but here it is like that lower RPM itself, it had become sort of a reddish, but red hot caps could be withdrawn, and in some cases we found that the drill edges which are formed were having absolutely no burr. So once we captured this phenomena or understood this phenomena, we try to model this by means of what is happening in the process of drilling. So if you take the thrust force remains steady up to a certain time, and then when this kind of a small, so what happens is here you are now cutting on a small triangular portion here, and you are feeding the tool by a distance of, say for example, whatever is the distance by which you are feeding, and now this opens up and then this breaks. So the energy required for breaking, bending and fracturing of the cup has been added here. So bending and fracturing has been added to get the total work of deformation. You don't want to go into details of this, but this is exactly the same physical phenomena you capture, and you try to put that into the model. Okay, I just want to go a little one more example, and a tapping example, and then maybe I'll stop with this example. So what we did is here we have done a tapping on the titanium, and then during the tapping, what we did was we have added two kinds of vibrations. One is called the axial vibrations. While we are going, we are having some kind of axial vibrations, and the other one is the torsional vibrations. Torsional vibrations in the sense you rotate forward, rotate backward, rotate forward, rotate backward. So every time you go forward, you come back backward, go forward, backward, forward, backward, something like this. So now this we call it as the one is that axial vibrations, and the other one is the torsional vibrations. So the axial vibrations and axial plus torsional vibration assisted tapping, that is where we wanted to take care of the spring back which is happening and which is gripping the taps while you are tapping the in the titanium alloy. So this is the experimental setup which provided the axial vibrations, and the radial the torsional vibrations were provided by means of the motor and rotating the drill in the forward and the backward direction. These are the details. Generally, we found that when you say continuous drilling, continuous tapping, and axial vibrations, then the most of your critical torque required reduces. And once your critical torque reduces, the possibility of breaking of the tap also reduces because of that. So your critical torque comes down because of these axial vibrations. Now, why that happens? That happens because so for example, in the forward cut, you have formed a chip. So this is this is the chip which is formed in the forward cutting, when the tap is rotating in the forward direction. While you are coming back, the material which is behind the tap cutting edge has actually sprung back. So what happens is that you have moved, your cutting edge has moved, but the flank surface of the tap gets gripped by because of the spring back of the material. The body material comes and grips it, but you are coming out and then you are removing the sprung back material again. So what happens is that initially a big chip is formed, but when you go back and come back again, the sprung back material is also removed because of the second movement in the forward direction. So so you are making two chips. One is the main, and the other one is sprung back material. So while you are coming back and going forward, because of that action, one additional action and additional cutting, the taps won't get jammed inside the mm, uh, inside the inside the holes. So that is where and of course the axial vibrations are there which are given to the work surface. But this is what is the principle, that you try to understand the physics of the process, and then you will be able to find the solutions. You will be able to find the remedies for improving the machinability. Yes, so I'll stop here. I think I've taken about 50 minutes, and I'll leave myself for questions, any questions and discussions.
Yeah, thank you, Professor Joshi, for the wonderful talk. I got amazed to see that the deep insight that you have made for the three different cases, like machining, drilling, and then tapping, for the machining of the titanium alloys and all. Before I, the proceed to the audience for questions, I do have some, the questions from my side.
Sure.
So you have, the done experiments for the listening of different compositions, different environments, and also the process parameters. And you have engaged the quick stop freezing, the chip freezing mechanisms and all. So how fast this mechanism, engagement and disengagement, and also how do you control that, and to ensure that the heat which is getting generated, so that process gets repeated uniformly.
So one is the acceleration with which you withdraw the tool. So what happens is that when see, what happens is that there is a body here, the tool is brought up against a spring here. So there is a when the tool is brought up and it is put under the shear pin, it is actually compressing a spring while it is being brought up, and then there is a spring here. I mean the pin here. So there is a compressed spring here, which itself expands the moment the shear pin is broken. It requires a almost like 10 kg hammer, at least 5 kg hammer blow from the top. See, people have many devices, they have explosive devices, but I found that a simple hammer is the most important thing. The stored energy of the spring is the most important thing. You have to have a calculated calculate the spring constant and its energy, and then the hammering energy and the energy required for the breaking of the shear pin. So it has to be done so instantaneously. I forgot the amount of acceleration it requires, but then only you will be able to leave a frozen chip on it. Otherwise, the chip will be cut off from the machining. I mean the surface itself. You will not get frozen chip. The tool has to be withdrawn very instantly. So that's a device we had made and long time ago, and which we actually made very good use of that And what was the
Excellent.
second question?
No, that's the question.
Yeah.
And another thing is that you said about the different compositions also play. I mean, that's common sense that different compositions will play the role for shaping the geometry of the chip and all.
Yes.
So can you just tell us like which compositional factor is the crucial for in this case for the determination of shape of the chip?
So basically, there are like the factors. If you want to see, then you have seen that there is a fracture length and there is a shearing length which is happening. So depending on which is more prominent, if it is a fracture, then you require very little energy for that purpose. But the shearing which is happening and intense friction which is happening, that consumes the maximum amount of the energy you provide for the machining of titanium alloys. And why the cutting forces vary significantly? It is because that there is a fracture and there is a intense friction, fracture and intense friction which happens simultaneously. So so the factor is this, that we try to control this fracture length and shearing length. We try to reduce the shearing length, and our endeavor is that the the deformation should be uniform across the chip segment. You should not form the what is called as that concentrated shear localization. The shear should extend over the entire material so that there are no shocks in between. And that's where we try to reduce the temperature, we try to increase the temperature, we do it at room temperature. But I think there are certain advantages of doing it at LN2, because the fracture content of the process chip segmentation increases, your energy requirement comes down, the segmentation is not completely discontinued, but their segments are joined together. But the extent of what we were saying, the crushing of the segments, that inter-segmental friction comes down significantly. So LN2, I mean, cryogenic cooling helps in a number of ways in this material, machining of this material.
And in case of the tapping operation, the for the axial vibration and all, so you have given amplitude beyond the 11.
Yes. Again.
The phenomena gets totally opposite.
It is again. You have. I mean, you kind of overlap the machined surfaces. I mean, you come too far, and that's where the amplitude of that, when it increases, then there is a problem. So you have an optimal there. So within that, you have to operate so that you don't you have a secondary chip which is also removed during the process.
Thank you. Yeah. So I think there are some questions in the chat box.
Please. Shall I stop my sharing screen, or maybe required? I will share again if required. But
please. I request you to go through the chat box.
Okay.
There may be some questions.
Okay. Just chat box. Okay. Gupta from USA. Midhani, Hyderabad, only producer so far, and I designed.
So I request the participants to put your questions in the chat box, if any. We do have still 1 or 2 minutes left.
No, he is asking, are you a bona fide metallurgist? No, I am not the bona fide metallurgist. I in such cases, I am a machinist, but I take help of my colleagues who are good in metallurgy, so that they help me in the other part. So I collaborate with, most of the time I collaborate with the other faculty members who are expert in their fields. But I'm a kind of, in the machining field. So that's where. So I'm not a bona fide metallurgist, that I can tell you.
No, but you are in the field of machining, that is okay. But you have done a tremendous amount of investigation, about the process.
Correct,
I really got amazed to see that. Every moment capturing the image from the memory.
Correct.
It's a wonderful investigation.
Yeah.
If any question is there from the audience participants, please quickly write in the chat box. Yeah, sometimes we do experiments, but we forget to take a minute look about
Look
what
at
is.
that. Yeah.
So
So
you have rightly mentioned at the beginning that seeing the type of chip it is getting formed, you can make a comment on
yeah,
what's this workshop.
correct. Yeah, correct.
Absolutely true. I fully agree with you.
Yeah. So actually, we throw away the chips in bulk,
Yeah, yeah.
but if you just simply take those, even the color, some professors have done analysis of colors of the chips, and in fact now you can see that red burned chips in the drilling process, they
Yeah,
indicate the burned chips indicate that there is an increase in temperature. Yeah.
yeah. No, but your study is very, very in-depth study. Very, very in-depth study. Your
Thank you.
scholars have done
Thank you.
scholars have done a wonderful job. Yeah. I think there is no more question from the.
Okay, good,
Yeah.
good. Yeah, I think it's a
One
sort of a
question has,
traditional area. People
no, one
have.
question has come up from Deepika Gupta. Can you
Okay,
please explain in detail how is the low conductivity affecting the elongation of grains?
okay. So low conductivity is not affecting the elongation of the grains, but low conductivity is is restricting the heat generation because of the friction. Is restricting the flow of the heat in all the directions. So what happens is that the heat remains concentrated in these zones. Yeah, and that's why there is a localized deformation of the material rather than the complete body of the chip is not deformed. The body of the chip, if you see the microstructure and grains, those grains are of intact, sort of intact. They are of regular size. Only the grains between them they get crushed, and that's the difference it makes. It doesn't elongate the grains. It elongates the grains which are on the. You can see the evidence that grains are getting crushed by seeing the grains which are elongated along the segments. So on the edges of the segments, you find the grains are getting elongated, and inside that there are grains which are almost like intact. And just go a little further, you find that the grains are crushed to a very very low size.
But the size of the grains also does vary with the environment because you have considered the
Yes.
LN2 and then hot, high
Yes.
temperature.
So now those things are all parameters are also there. So I have just presented only one case to just to say, to make the students aware that why these alloys are difficult. These
Yeah.
alloys are difficult because there is a severe crushing which is happening in the while the chip is getting formed, and the time constants of that crushing is so small. So the entire energy you provide is actually getting into that crushing. So we say, oh, it's very difficult to machine. Why it is difficult? It's because these phenomena which are happening there, they are so difficult, so different from the regular materials, and that's why it is difficult. Yeah, so yeah, somebody has saying that much over the actual average machining can also be replicated by Charpy strains. Yes, I think yes, some of the older times the Charpy type of fracture tests have been done. Only thing there is that the the kind of sustained effect of temperature which happens in a machining process, like when the machining process comes to a steady state, there is a rise in temperature, and apart from the strain rate, temperature also plays a very important role. Whereas the testing of the material, if you take test, it's a very fractional kind of operation, and the temperature effects are not taken into it. Also, I am not very sure if strain effects are taken. The strains which are there in a machining process, they are anything between 2 to 8. I think those strains are very very magnitude of strain is very difficult to replicate in a testing environment. So temperature effect and strain effects, so you cannot replicate. So you actually go to the machining process itself and use the machining process as a test itself, and you capture it, those movements at a particular moment, and then you perform the measurements on those and try to understand. So that's where this is done.
Professor Joshi, since you have, as you have said that the machining of titanium alloy is different from the conventional material. So, what is your comment on the tool geometry?
Yes.
Are they?
So somebody is asking that the tool geometry. See, the point is that we are not checked much, but the geometry per se, the rake angle and all that could definitely influence, because the rake angle will definitely influence the position and the stresses we are applying while you are on the shear plane. So, but I think that the inherent mechanism of chip formation is so dominant that a small change in the geometry doesn't really affect this whole process, because the energy consumption which happens in a shear band formation is so large that it is not likely to differ significantly by changing the the geometry of the tool.
But in case of drilling, you have shown that.
Yes, in case of drilling, yes. In case of drilling, it is there. That is because that's because we have what we have done is that we have tried to we have seen that there are two places the cap was breaking, and those corners which were there, one is a chisel edge corner and the other one is the drill corner. So we cut off those, we just soften those two corners, and that actually helped us to reduce the burr formation. In fact, you will know that whenever components made of titanium alloy are, wherever there are made, whichever company, they have a deburring section. They have 100%. There is a massive deburring section in those companies. It is not easy to make a burr free completely. There has to be a massive deburring operation, and complete burrs have to be removed. So it's a job. It's a sort of a job.
Yeah, Professor Joshi, two more questions are there
Yeah.
from Ms. Deepika Gupta. Like for EBSD, electropolishing has to be
Yes,
performed.
it has to be performed there. Yeah. So now what happens is, see, while you are deforming the material, you apply so much forces, so much strains and temperatures. I mean, polishing is nothing. Polishing strains are and all those things are very, very negligible. Of course, polishing will do what surface grains deformation at the most some extent, but it doesn't affect much, because you already strain harden the material, make it so strong while you are, because of the strain hardening, that polishing strains are comparatively very, very low.
The other questions from Deepika Gupta is answered. The tool
Chips appear that only orthogonal tool is used for machining. Have you used other geometry also? So what happens is that if you make a three-dimensional cutting, the chip geometry becomes complicated, and so you try to make it slightly simplified, so that you can simply relate the initial thickness of the layer which is removed and the chip thickness. You can relate those very easily in orthogonal cutting. So on a first level, if you want to do that, let's avoid the complications of third dimension, three-dimensional, and that's where we perform the orthogonal machining operation, so that you can simply take the layer which is removed, the geometry of the layer or thickness of the layer, and the thickness of the chip which is generated. It becomes easier.
Yeah, another question from Rishabh Sarankar is that in case of chamfering the tool tip in drilling operation, how can we compensate the force required?
No, it is not like this. What happens in a drilling operation is that the chisel edge is a sort of a straight part of the drill, and this chisel edge being a kind of a horizontal, you are kind of deforming the material. So the moment you reduce the length of the chisel edge, you actually reduce the thrust which is happening. Now Now, when you reduce the thrust, that means the bending which is happening. So at the end of the drilling process, when the thickness of the lower plate becomes smaller and it starts bending, that bending can be avoided because you are reducing the thrust. So in this case, the effort was to reduce the thrust, and if you want to reduce the thrust, you have to reduce the length of the chisel edge. That is the first thing. So once you reduce the thrust, once you reduce the load or the thrust on the, then bending happens less. So bending happens less, that means your cutting will continue. And those triangular sections at the end of the drill, you will continue to cut because they are not bending now. And once you start cutting them, and they are not bending, so that means they are not going away from the drill. If they go away from the drill will not be able to cut, because drill is coming by a certain distance in every revolution. Because the tool has workpiece has bent further, it will not cut it, and then larger burrs will get formed. So the intention is that what happens is the bending happens first and then cutting, we try to cut it. It should not happen. The plate should remain stronger, and the cutting, so that the cutting should happen and the bending should happen later on. So that is where the thrust has to be removed, so that it doesn't bend, it gets cut. So the more you cut, the smaller burr it will form on the corners.
I think there is no other, the questions. Yeah.
UTS is low strain.
Yes, just
Strain rate is high. Strain rate, I am not doubting. Strains, amount of strain you provide during the cutting process is very high, and that is something which is very difficult to emulate during these processes. Okay.
Yeah. So I think that's over. Yeah, Professor Joshi, it's a really wonderful interaction.
Thank you.
Really
Thank
wonderful
you very much.
interaction.
Yeah.
And we must continue. I mean, we must have similar interactions in future as well.
Definitely.
Students will be enriched.
Thank you very much for calling me and giving me opportunity.
No. It's our, it's our honor that you have taken out time, and then you have enriched us, from your research and all.
Sure.
Thank you so much for your presence.
Very much. Okay. Welcome.
Yeah, I request Ananta to let us know the speakers about the others. Yeah, thank you, Professor Joshi.
Okay, thank you very much. Yeah, right. Okay.
Yeah. So the Ananta, could you please let us know the so on 16th, yes, Professor Satyendra Gupta would be there, and then Mr. Dipankar Ghosh on October 23rd, and then next 30th of October is the Arjun Malhotra would be talking about scope and opportunities of the entrepreneurship in product design and manufacturing. With this, we'll finish the month of October, and we are also getting scheduled for the month of November. All our videos, the webinars are recorded, so anybody can watch through for the past videos and all. We'll also send you the link for that. The same.
Please. Thank you again, and bye. Good night. Bye.